In Unit 7, we're going to discuss systems of objects, specifically how forces can change the motion of systems of objects. And in Section 7.1, I'm going to cover systems in a conceptual way. Section 7.2 will feature some numerical examples. Most of the things that we've been talking about and referring to as objects are really just combinations of smaller things. An object is something that doesn't have an internal structure, or at least we pretend that it doesn't. We don't worry about what's going on inside of it, we just worry about the motion of it as a whole. And really, only things called elementary particles can't be considered as anything other than a single object. We know that they do not have any internal structure, and these include things like electrons and quarks. Quarks are what make up protons and neutrons. But we can treat collections of objects as though they are a single thing, and we refer to that single thing as a system. And this is especially useful when we are concerned with a system of connected objects, where the objects are going to share the same speed and the acceleration as they move. And these are two types of typical connected objects problems. The first type, you can see we have two boxes that are connected by contact. If they're pushed to the right, they're going to both move to the right with the same speed and acceleration. Or we can have objects like our four penguins here connected by a rope. We have to distinguish between internal and external forces when talking about the motion of systems. External forces are exerted on a system or a part of the system by something that's outside of the system of objects that we're considering. Only external forces are able to change the motion or accelerate a system of connected objects. In contrast, internal forces are not able to affect the motion of the system as a whole. They can affect the motion of objects contained within the system, but as a whole, internal forces, which are forces that are exerted between objects within the system, cannot affect the motion of the system as a whole. Here's an example. Here we have an astronaut in the International Space Station, and he seems to have found himself stuck in the middle, floating around. And the astronaut is a system, right? He's made up of cells that make up tissues that make up his arms and legs. And no matter how he moves his arms and legs, he can't seem to accelerate himself. There has to be some external force to push him towards the walls. But why aren't internal forces able to affect the motion of the system? Well, it's because they always form a Newton's third law force pair. And to remind you of what Newton's third law says, it states that all forces are always going to act in pairs. And the agent and object are going to experience forces that are equal in magnitude and opposite in direction. So if the internal forces are exerted between objects within the system contains both the object and the agent. And so these two forces are always going to cancel each other out for the system as a whole. So here's a counterexample. This is going to look weird because it's not good physics. It's good old Coyote and Roadrunner. Here you see the coyote has strapped an outboard motor to himself and is pushing on a tub of water that he's dragging along. Now, obviously, that can't really happen. And why can't that happen? Well, let's look at this example in a little more detail. We have two objects that are contained within our system. As a whole, you're going to see that the forces should cancel out, and he should not be able to accelerate forward. The outboard motor is pushing backwards on the water, and in turn, the water is going to push the coyote and motor forward. This is what a boat does. The boat pushes backwards on water, so the water pushes the boat forwards. But what the coyote made a mistake when he connected himself to the wash tub full of water. where there's going to be an equal and opposite tension force. And so when we look at this as a full-on contained system of objects, the water on the motor and the motor on the water are going to cancel, and then the tension forces are also going to cancel. And so overall, the total force on the system is zero, which should mean that the acceleration of the system should be zero. That's why this looks so funny. In another example, you can see that we have another Coyote and Roadrunner cartoon. This time where the Coyote is trying to use a self-powered fan. The fan pushes the sail forward to try to catch the Roadrunner. This is obviously not good physics. Why not? Well, we've got the Coyote, fan, and the sail, but in between the fan and the sail is some air, right? So that air moves along with the Coyote, sail, and fan. This is all part of the same system. So the air pushes the sail forward, the motor pushes the air forward, and the sail pushes the air backwards. Notice that this is a Newton's third law force pair. So as a system, with the system as a whole, these two forces are going to cancel out. And then the air would push back on the motor. And again, we have this Newton's third law pair. These two are going to cancel each other out. So as a whole, the force on the system is zero. So the Coyote, fan, and sail should not accelerate forward. In this example, we're to draw a free body diagram for each of these three blocks shown, and we're supposed to ignore friction, drag, and any vertical forces like the normal force and their weight. So we're going to draw each box and display the forces acting on each box. So the tension in string 1 is going to pull box marked M1 to the right. Box M2 is going to get pulled to the left by T1, the tension in string 1, and it's going to get pulled to the right by the tension in string 2. Box 3 is going to get pulled to the left by the tension in string 2 and to the right by the tension in string 3. And part B of this wants us to identify the forces as either interior or exterior forces. And you can see here that T1 acts between objects within our three-block system. That makes them interior forces. Same thing with T2. T2 acts between blocks 2 and 3, and so that's an interior force. But T3 does not act between two boxes. That's an exterior force. And so T3 is able to accelerate the system. T2 and T1 are not able to. Now, in ranking the strength of the tension in each string, obviously the whole system is going to move to the right. So focusing on block 3, tension 3 must be bigger than tension 2. There has to be a bigger force to the right to accelerate the block to the right. And we can continue this line of logic. If we look at T2 and T1, this block is going to accelerate to the right, so there has to be a larger force on it to the right than to the left. And so T2 is going to be greater than T1. In this last example, we have two blocks, A and B, that are pushed to the right by an applied force, F sub A. We're given that the mass of block B is greater than the mass of block A. Part A wants to know for which, if either, of the two situations below is the magnitude of the acceleration greater. So we're told to compare the accelerations. The important thing to realize is that the applied force, which is the same in either scenario, is the external force. And so if we take Newton's second law, the acceleration is the net force divided by the mass, well, the net force on the system is really just the applied force. And the mass of the system is just the mass of block A plus the mass of block B. By the commutative property, this denominator is going to be the same regardless of the order that the two blocks are put in. So the applied force is the same, the denominator is the same, therefore, in either case, the acceleration is the same. All right, for part B, we want to know in which situation is the magnitude of the contact force between the blocks greater. So for this, we're going to need some free body diagrams. So I've drawn the boxes, and I've drawn them a little bit separated so that the arrows for the forces are not going to be drawn right on top of each other. So in the first situation, the applied force is exerted on block A, where the applied force is exerted on block B in the second situation. The contact force between the two blocks is going to be pushing the first block in the pair to the left, and the contact force will be pushing the second block in the pair to the right. And what's important to remember is that the acceleration is the same in both cases. And so in this case, the contact force is the net force on this. So the net force, which is that contact force, I'll just call that F sub CON for contact force, is going to be the mass of block B times the acceleration. Over here, the contact force is again the net force on that object, and that's going to be the mass of block A times the acceleration. So which of these two is larger? Well, hopefully you've realized that the mass of B times the acceleration is going to be a bigger number than the mass of block A times the acceleration, because the acceleration has the same value in either situation, but the mass of the second block is larger in the first situation. So it is the magnitude of the contact force will be greater in situation